Welcome back. Today we are exploring one of the most fascinating aspects of LLM development scaling laws.
Scaling laws are mathematical relationships that describe how model performance changes with scale, model size, data size, and compute. These laws have been incredibly influential in guiding how companies build LLMs and where they invest their resources. Let's start with the fundamental question: what happens when you make a language model bigger?
Early neural network research found that performance improved with size, but the relationship wasn't well understood. Then in 2020, OpenAI published a paper on scaling laws that changed everything.
They showed that loss, the prediction error of the model, follows a power law relationship with three factors: number of parameters, amount of training data, and compute used for training.
A power law means the relationship is predictable and smooth. Double the parameters or data, and you get a consistent improvement in loss.
This was remarkable because it held across many orders of magnitude. From millions to billions of parameters, the relationship stayed consistent.
The key finding was that bigger models trained on more data with more compute reliably perform better.
But here's the crucial insight: these factors aren't independent. For a given compute budget, you need to balance model size and training tokens.
The original scaling laws suggested that model size was most important. Bigger is better, and you can get away with training on relatively less data.
This led to the era of giant models. GPT-3 has 175 billion parameters trained on about 300 billion tokens.
But in 2022, DeepMind published the Chinchilla paper that revised our understanding. Chinchilla scaling showed that previous models were undertrained. For a given compute budget, you should train smaller models on more data. Specifically, the optimal allocation is roughly equal compute spent on parameters and on training tokens. If you have 10x more compute, you should increase both parameters and tokens by about 3x each.
Chinchilla itself had 70 billion parameters, but was trained on 1.4 trillion tokens, many more tokens per parameter than GPT-3.
And despite having fewer parameters, Chinchilla outperformed much larger models on many benchmarks.
This insight shifted the field. Now companies focus on both scaling up parameters and training on more tokens.
Models like LLMA, Mistral, and others follow Chinchilla scaling, training on trillions of tokens.
But scaling laws aren't just about final performance. They also let you predict performance before actually training the model.
If you train a small model and measure its loss, you can extrapolate to predict what a larger model would achieve.
This is hugely valuable because training large models is expensive. Scaling laws let you make informed decisions without exhaustive experiments.
The relationship between loss and compute is particularly elegant. Loss decreases as a power law in compute. LLA say as where C is compute, A is a constant, and AKA is around 0.05 to 1.
This means diminishing returns. Each additional order of magnitude of compute gives smaller absolute improvements.
But even small improvements in loss can translate to significant improvements in downstream task performance.
It's important to note that loss is measured on next token prediction. How does this relate to actual capabilities?
Interestingly, many task specific benchmarks also scale predictably with loss. As loss decreases, accuracy on question answering, summarization, and other tasks tends to improve.
But some capabilities emerge suddenly at certain scales. These are called emergent abilities.
For example, few shot learning, the ability to learn from just a few examples in the prompt, seems to emerge around certain model sizes.
Chain of thought reasoning, where the model shows its work step by step, also emerges at larger scales.
There's debate about whether these are truly emergent or just rapid but continuous improvements. But either way, scale unlocks new behaviors.
Now let's talk about data scaling specifically. How much data do you need?
The chinchilla scaling suggests you want roughly one token of training data per parameter, or even more for optimal performance.
But we're starting to run out of high quality text data. The entire internet has been largely scraped for training.
This has led to interest in data quality over quantity and in synthetic data generated by models themselves.
There's also data curation, carefully selecting and filtering data to maximize value per token.
Deduplication is particularly important. Removing near duplicate data prevents the model from memorizing repeated content.
Some research suggests that seeing the same data multiple times, multiple epochs, can be acceptable if done carefully, though one epoch training is generally preferred.
Now, what about scaling beyond parameters and data? What about architecture improvements?
This is an active area of research. The scaling laws we've discussed assume a fixed architecture, the standard transformer.
Better architectures could shift the curves, more efficient attention mechanisms, better normalization, or improved activations might give better performance for the same compute.
There's also algorithmic efficiency. Better optimization algorithms or training procedures could extract more from the same data and parameters.
Another dimension is test time compute. Most scaling laws focus on training compute, but you can also scale up inference.
Techniques like generating multiple responses and selecting the best or using more inference time sampling steps can improve performance without changing the model.
We'll talk more about test time scaling in phase 4 of this series.
Let's discuss some limitations of scaling laws. First, they describe averages across many tasks, not performance on any specific task.
A model might follow scaling laws on average but still struggle with particular types of problems.
Second, scaling laws typically measure loss or perplexity, which are proxies for real world usefulness.
A model with lower loss isn't necessarily more helpful, harmless, or honest.
Third, scaling laws don't account for things like bias, safety, or robustness. Bigger models can amplify biases present in training data.
And there are diminishing returns. Going from 1 billion to 10 billion parameters gives a big jump. Going from 100 billion to 1 trillion is much harder to justify economically.
There's also environmental and economic cost. Training the largest models requires millions of dollars in compute and significant energy consumption.
This raises questions about who can afford to train frontier models and how to make AI development more sustainable.
Some researchers focus on efficiency, getting the most out of smaller models through better training, distillation, or architecture improvements.
But the scaling laws remain a powerful framework for understanding LLM capabilities.
They tell us that within the current paradigm, scale is a remarkably reliable path to better performance.
And they've enabled a kind of predictability in AI development that wasn't possible before. Companies can forecast what capabilities new models will have based on their training budget.
So, to recap, scaling laws describe power law relationships between loss and parameters, data, and compute. Chinchilla scaling emphasizes training on more tokens per parameter. These laws enable prediction of model performance before training. Emergent capabilities appear at larger scales, and there are important limitations around cost, sustainability, and real world usefulness.
This concludes phase 2 on the core mechanics of LLMs. We've covered tokenization and embeddings, attention mechanisms, pre training versus fine tuning, and now scaling laws.
Next episode, we're starting phase 3 on transfer architectures. We'll dive into evaluation metrics, how we actually measure LLM performance.
Thanks for listening.
Until next time, keep learning and stay curious about AI.